I'm Wally from Blackdot Energy, and this is the technical maintenance PIMD video on the solar system for David Webster. These videos, the intent is to explain the system technically, because service delivery is key for WITS. That at any point we have hot water available, and enough hot water available where possible, at least within WITS's control, to ensure the highest service delivery for the students. This specific video, we're going to explain to you the hydraulic concepts behind the solar system, and it's one of 6 videos explaining the technical detail of the system. Basically, all the controls of the hot water plant is within this cabinet. So I'm going to remove the lid, and then we'll start with explaining the detail inside of the solar controller. So usually this lid is fastened with 4 screws on the 2 outside edges. For the purposes of this video, I removed that before the time. So the hydraulic concept behind the design of the solar is as follows. The primary heating of our 10,000 litre storage tank is in fact from the solar system. It's 128 square meters of solar collectors, and it is an indirect heating. In other words, the water that's in the solar collectors is not the water that's circulated through the tank. It's a closed loop. So we've got a glycol liquid. It's like an antifreeze that you find in a car, but a food grade glycol, which then isolates the circulation cycle from the solar collectors separate from the tank. And that's done through a plate heat exchanger, which is in the back section of this unit. So we've got an indirect transfer of that heat or energy from the solar collectors over to our tank. So from the tank, we have a circulation that brings water from the tank into the heat exchanger, and also a circulation that brings the water from the solar collectors into the heat exchangers, and that heat transfer then happens towards the tank side. You'll see the circulation pump at the top, and that basically circulates the water on both sides of the heat exchanger, transferring that energy. The way that this is done, because we have a glycol, it gives us a freeze protection on the system, so during the coldest parts of winter, that we don't have the liquid freezing up, but it also again protects overheating as well. Because we've only charged the system once, we keep all that municipal dirt and debris that comes through the municipal water, we keep it out of the solar system. In this way, we in fact ensure that we've got an expected life of over 20 years with a solar plant. But again, this video is to explain the mechanical concepts of it, but really the maintenance and the fixing of the system needs to be done by a specialized solar contractor. But again, if something goes wrong, this will show you the components and what are the errors involved with it. So what we've got here, we've got temperature gauges that shows you the incoming and outgoing temperature. So here at the bottom we've got our pressure gauge, again showing that the system is 3 bar. You'll remember with the first video we did with the tank to do the initial checks, the water on the opposite side, in other words the building, also runs at 3 bar. So both sides, solar plant and on the water supply part, it's 3 bars. Then we've got our temperature. So currently the temperature that goes to the solar collectors is 35 degrees, and the temperature coming back is in fact 65. Believe it or not, it's now the 27th of June, so it's midwinter, and we're still getting phenomenal heating out of the system. Then what we've got is our Technique Alternative controller, gives us all our displays. So inside the cabinet we have got a little chart. This same chart is also on the wall mounted display board in the plant room, and basically if we scroll through these, you'll see that T1, T2, T3. So T1 is the temperature on the collector panels, which is currently 71. If we scroll left, T2, that is the temperature at the bottom of our storage tank, that is 48 degrees. T3, that is the temperature at the heat exchanger, that is at 63. T4, that is the temperature at the top of our storage tank, that is 63. T5, that is again the temperature at the bottom of the heat exchanger, that's 46, that's inside this unit here. and that's basically the rest of these gives us how much energy has been put into the solar system. So that's how you can do a quick visual analysis, either through the temperature and pressure gauges or by just scrolling left and right, giving you the displays and what temperatures is going into the system. And this is a visual functional check to see is the system operational and if there's power on this. If there's no display, the very first point where you check is again similar to the gas controllers. We go to the main DB board in the plant room to ensure that there was no trip breakers, that we've got power everywhere. So that's the first check if there's no display. Secondly, if we see with the displays that no temperature is coming in, check the pressure. If the pressure has got an error, it means that at some point the system has gone in over stagnation and it's the safety valve open and it released glycol. At the bottom of the system, I'll show you now, we've got a glycol overpressure tank, and there you'll be able to visually see if there was a discharge of the glycol fluid, you'll be able to identify where this fluid has gone to. How do we protect the system? So there is periods, for instance, over the December holidays where we cannot switch off the sun. It keeps on heating, but we don't have students or consumption of the hot water. The way that the system is protected is that we have in fact got a membrane expansion configuration so that if the system goes into stagnation, stagnation means that from liquid it goes into steam and it overheats, that we can then totally displace that entire volume into the overpressure tanks. So let me go and show you the overpressure tanks and where and how we protect the system again of stagnation. So how we protect the system during stagnation is in fact the membrane expansion vessels that you see here has got a rubber membrane inside. One half is liquid, the other half is air. So within these two membrane expansion vessels, we can in fact accommodate the entire liquid volume out of these solar collector plants. So the entire 128 square meters of solar plants, if it goes into steam, we can displace the entire volume from the solar plant into these membrane expansion vessels. It will condensate again and the water will then flow back into the solar collectors. So through that expansion, we can then protect the system. What you see here is a grey tank, and in fact it says pre-cooling tank. So what we've learned over all the years of having these commercial solar plants is this is a little trick of the trade. So what we do is this is filled with cold water. So when it in fact goes into stagnation and it displaces the liquid in, what we do is into these membrane expansion vessels, we in fact displace cold water so that we don't get the flaming hot water from the solar collectors hitting these rubber membranes. But in fact, we displace it with the cold water, the system can then condensate again and it can go back into the plant room. The other point that we need to just show you quickly is the safety release valve. And if that has triggered, how to just reset that. So let's say you get to the plant room and there's water that's spurting out of this plant room. The only point that can happen is there is a safety overpressure valve which releases the hot water. So not the glycol water, but the hot water. And that valve sits over here. If there's been a pressure imbalance or the pressure has exceeded 3 bar, what will happen is this valve will open up. And that's basically what you'll see. You'll get into the plant room and that will happen. So if the safety valve goes open, it releases the pressure out through that. The way to reset it is to really just turn that button. So if you turn that button, so when you've reset the valve, it gives you the opportunity to get the contractor out to replace it. The reason why we say replace is because the valves are really intended as a safety valve and only open up once. In our discussions with the PIMD team at WITS, or the maintenance teams, the suggestion was in fact that we leave a spare safety valve inside the panel here, so that if the safety valve has failed for whatever reason, it is easy for a plumber or contractor to replace it because it's just a thread on both sides and you can replace the valve. So in future, the intent is that there will be an extra safety valve in this cabinet as a spare, so that if that valve is opened or it's failed, it's very easy to replace. But you'll identify that with the water that has come out of this pipe. Previously in the video I mentioned the glycol overpressure, so this was again on the hot water side with the tank. On the glycol side, the Solix side, if for whatever reason the expansion tanks could not protect the system, there's a safety valve that at the back, so if the expansion failed, the safety valve will open up and the glycol liquid will be displaced in this tank. The reason why we've got a tank is for two. Number one, you can visually see if the system has displaced glycol, that you can identify that there was a problem. And secondly, the glycol is quite costly, that we can use the same glycol to recharge the system and at least see we've lost 1 liter or 5 liter. This concludes our solar video. Again, it gives you an explanation of how the system works, but the intent is that you get the specific contractor out to come and fix any problems in the system. Thank you for watching the video. Also watch our other technical videos to really bring you to an advanced level of understanding the maintenance and the technical components of this hot water plant for David Webster residences.